Hello everyone, welcome to another lesson in physics. Today we're picking up on mass versus weight. We're going to, through this lesson, differentiate the difference between mass and weight. Because in everyday speak, we usually kind of switch these two up and don't really talk about the difference. Alright, so let's start off with this example right here. So we have a block of wood is sitting motionless on a table. What forces are acting on it? So we have two forces that are going to be acting on it. So the first one is going to be weight. So we could draw this in. We have this weight force, which we'll call Fg, since this is the force of gravity pulling down on it. Then upwards, we are going to have this other force, because if it's just the one force pulling down, then it would go through the table, so we need another force pushing up. And this is going to be the force of the table pushing up on the block, which we call the normal force, which we can write as Fn. So this first one down here, call weight. Up here is the normal force. And weight is the force an object experiences due to gravity pulling it toward the center of the earth. So that's the one that pulls down, and then pushing up. The normal force is a reaction force that any object exerts when pushed on. So when you push on something, you will feel that object or surface pushing back, and that is called the normal force. So when differentiating between weight and mass, we should define what each one is. So when talking about mass is the amount of matter contained in an object. So something that's inherent about mass is that this is going to remain constant no matter where we bring the object. If we bring it into space, it's still going to have the same amount of mass. What's going to change, though, is going to be weight. And weight is defined as the force of gravity on an object. So weight is going to vary with gravitational field strength. Which is actually our good friend, little g. So to write this out, and what this is equal to, so our force of gravity, which we call Fg, this is our force due to gravity. It's going to be equal to our weight, which is sometimes written out as a W. It's our weight. Which is the force due to gravity. So they are the same thing. And this is going to be equal to mg, which is the mass times our little g, which is minus 9.81 meters per second squared. All right, so that's going to be how we find the force of gravity or weight on any single object. So let's take an example right here. So we have an astronaut that weighs 750 newtons on Earth. What is the mass of the astronaut? So we can use our formula from before. Force of gravity was mg. Now we can rearrange our letters. So mass equals Fg over g. And we can plug in some of our numbers. So the mass is going to be equal to 750 newtons. And since this is on Earth, then it's going to be 9.81 meters per second squared. Now we can say both of these are down, that the force of gravity is down, acceleration is also down, or we can just keep them both positive in this case. Either way, it'll give us the same answer. Then we can find that his mass will be equal to 76.45 kilograms. All right, and that's how we would find the mass of an astronaut from the force due to gravity. Now, let's determine the weight of the astronaut on Mars, where the gravitational field strength is 3.67 meters per second squared. So the first thing we have to remember is that mass is going to stay the same, so we can use that mass from before. Doesn't matter what planet he's on, the mass or the amount of matter that makes him up is going to stay the same. Then we can use our equation, Fg equals mg, force of gravity, which this is the same thing as weight, so we can either call it W or Fg. It's going to be equal to the mass, which is 76.45 kilograms, times gravitational field strength on Mars, which is 3.67 meters per second squared. Which the gravitational field strength is the same thing as the acceleration due to gravity that we've seen before, just slightly different meanings to it, but the same number. Right, so when we plug in our numbers, we will get 280.6 newtons. So we can see how that compares to Earth, where Earth, his weight is 750 newtons, and then on Mars, he'd be lighter, 280.6 newtons. But the mass will stay the same. Alright, let's take a look at another example. So now we have a glass bottle with a mass of 10 kilograms is sitting on a counter. So what is the bottle's weight? So we can use our formula from before, that our weight is going to be equal to the force due to gravity. It's going to be equal to mg. So we can plug in for m, where this is 10 kilograms. And then our gravitational field strength, or acceleration due to gravity, our little g, which is 9.81 meters per second squared. So we get our force due to gravity on this glass bottle, or its weight, is going to be equal to 98.1 newtons. Alright, so now we want to know what force does the countertop exert on the bottle. So as we said before, there are two forces acting on here. The first one is going to be the force due to gravity, or its weight, and then there needs to be another one pushing up to keep it in place in that one spot, which we call our normal force. Now, a common mistake that I often see is people calling the normal force the natural force. The reason it's called the normal force is, maybe you learn this from math, what it means for something to be normal to a surface. That means that it is 90 degrees from the surface. So if we have a surface at a slant like this, we'll see that our normal force is always going to be 90 degrees or normal to that surface. So it's called the normal force, not the natural force, as some students like to call it. So we can also calculate what this normal force would be. So if we're talking about the bottle's weight, we should include that it'll be negative because it's going down. So our normal force is going to be equal to and opposite the gravitational force from above. So if it's going to be, you can write it out like this. The normal force is equal to negative the gravitational force, which will give us that it is a positive 98.1 newtons. Alright, so now let's take a look at Newton's third law. So we've mentioned the first law and the second law, so now we want to move on to the third law. And the third law states that every action has an equal and opposite reaction. And we'll see what that means in a second. So that means that forces occur in pairs. So if object A exerts a force on object B, then object B will exert a force on object A that is going to be equal in magnitude, but will be opposite in direction. So if we were to write this out, we could say that the force of A on B is going to be equal to the opposite of the force of B on A. So now I want to take a look at some of these action-reaction pairs. So here we have a swimmer. So when you swim, which way do you push the water to move forward? So we can see that the action force in this case is pushing backwards. So when we're swimming, we're actually pushing backwards in order for us to go forwards due to the reaction over here. Now, when you walk, how do you move forward? What if the ground under you moved? So, in this case, we also push backwards. And usually when we're walking, the earth itself doesn't move back. But if the ground also moved, then the ground will move backwards. So we have an example here of getting off a boat, that as you step forward off of it, the boat's going to move backwards and you're going to move forward. So there's always this pair of action and reaction. Now another example is going to be a rocket. So a rocket works on this same principle in order to get into space. So how do rockets move in outer space? So the way that this works is that they actually eject mass backwards. So we'll see that rockets move in outer space by ejecting mass backwards to move forwards. And this is due to this action-reaction pair. That with that action, the reaction is going to be the rocket moving forward in outer space, because they actually don't have anything to push off of because there's no air once you get into space. Alright, so let's take a look at some examples of Newton's third law here. So we have a 400 Newton girl that pushes a 1000 Newton sailboat with a force of 100 Newtons. What is the force of the sailboat on the girl? So there are a lot of numbers here, but it's actually going to be a little bit simpler than we think. So the force of the boat on the girl is going to be equal to the negative of the force of the girl on the boat, which is this force right here. If we call that positive, then we are going to get negative 100 newtons. And that's all there is to it. That's equal and in the opposite direction. So now let's take a look at another example. So we have a mosquito that hits the windshield of a school bus. So compared to the force of the mosquito on the bus, the force of the bus on the mosquito is, and you guessed it, that the answer is going to be the same. So the magnitude of the force is going to be the same. Although we will see that there'll be some differences due to their masses, but the force is actually exactly the same as the bus on the mosquito and the mosquito on the bus. All right, let's take a look at another example. So if a 65 kilogram astronaut exerts a force with a magnitude of 50 newtons on a satellite that she is repairing, the magnitude of the force that the satellite exerts on her is going to be equal to, let's take a look at this. So we have the force of the satellite on the astronaut. It's going to be equal to the negative of the force of the astronaut on the satellite, which we saw before. It's 50 newtons. So this is going to be equal to negative 50 newtons. That's all there is to it. All right, so that's it on mass versus weight and Newton's third law. I hope you all have a great rest of your day.